Welcome to this explainer. Today, we are unlocking the ultimate computer science Cambridge exam strategy. Think of yourself as a wizard, and structural frameworks are your magic spells. Cast the right spell, and you literally guarantee maximum marks for yourself. We are looking specifically at binary addition and overflow today, mapping this directly to syllabus codes 0417, 0478, 2210, and 9618. Imagine you're sitting in the exam hall. The clock is ticking down, the tension is high. We typically see two types of students taking this exact paper. Let's call them Alex and Sam. Alex is the overpreparer. Alex overloads his answers with raw computer science facts, dumping every single thing he knows about ones and zeros onto the page, but includes absolutely no analysis. On the other side, we have Sam. Sam rushes. Sam looks at the clock, panics, and completely misses the command word requirements in the prompt. If we look at their flawed answers side by side right now, they are bleeding with red pen marks from the examiner. Why did they lose marks? Because they didn't have the spell. They didn't have the framework. Today, we fix that completely.
Okay, let's dive into this roadmap, which will take us step by step from recognizing the digital problem to applying the ultimate exam checklist. We'll start by looking at why Alex's memorization fails, then anchor our theory in reality so Sam stops rushing and missing the point. We'll break down the exact methodology for your answers, highlight the pitfalls to avoid, and finish with a foolproof 4-prompt system that works like magic every single time you sit down to write.
Section 1. The rote learning trap. And why labels aren't enough. We start by confronting the biggest hurdle students face: memorizing definitions in isolation without understanding their actual application. This is exactly what Alex does. Alex has memorized the exact textbook definition of an overflow error. He knows it happens when the result of a binary addition exceeds the maximum capacity of the register, like an 8-bit register trying to physically store a 9th bit. But when the exam question asks to explain the impact of this error on a specific digital system, Alex just writes the definition again. It is incredibly tempting to just memorize facts as disconnected labels, but in Cambridge exams, this is a massive trap. You have to demonstrate analysis. You have to cast the specific spell that connects the fact to the scenario.
Consider this perspective from the people actually grading your papers. Generic responses rarely gain full marks. This quote, directly from the examiner's perspective, brilliantly illustrates the high stakes of generic answers. This is exactly where Sam falls down. Sam reads the question, sees the word overflow, and writes, "It causes an error," and the computer stops. That is way too generic. Examiners aren't just looking for you to parrot back a textbook definition, and they definitely won't reward vague guesses. If your answer could apply to absolutely any scenario without changing a single word, it is too generic. You might know the theory perfectly, but if you don't anchor it to the specific command words like evaluate, analyze, or describe, you are going to lose out on those top marks. Sam rushed right past the command word explain.
So, the crucial point is that short labels simply won't cut it. To reach the highest marks, you must use precise terminology, clear processes, and connection back to the scenario. This brings us to the strategy reveal. Top students structure their computer science answers using the PEL framework: point, evidence, explanation, link. Think of PEL as your primary magic spell for the exam. First, you make your point. Identify the exact issue, like an overflow error. Then, evidence. You provide the specific binary addition that caused the extra bit. Next, explanation. You detail why the CPU's specific architecture cannot physically hold that data. Finally, link. You link it back to the scenario, explaining how this causes the specific machine in the prompt to behave unexpectedly. This directly satisfies the Cambridge assessment objectives for analyzing and evaluating computer science concepts. Alex lacked the explanation and link. Sam lacked everything but a vague point.
Let's move to our next section and see how connecting binary theory to real-world environments actually makes the terminology meaningful. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the strategy. Theory without context is easily forgotten, but when you understand why a system needs these binary operations, the concepts stick permanently. We're going to apply the PEL framework to real-world scenarios. We need to decode the command words in the question, look at the context, and cast our structural spell. Whether you're dealing with syllabus 0417 or 9618, the examiner wants to see that you understand how an overflow error doesn't just exist in a vacuum, it exists in a physical piece of hardware trying to accomplish a real task.
The exact same patterns of binary addition and overflow appear everywhere. Here are the environments you'll likely see on the paper: smartphones, websites, school systems, industrial control, banking, secure communication, robotics, retail systems. Let's do a quick interactive check. You have 30 seconds on the clock in your mind. I'm going to give you 2 answers for an industrial robotic arm that experiences an overflow error. Answer A, the robot stops because the binary number is too big for the register. Answer B, an overflow error occurs, point, as adding the sensor's binary inputs generates a 9-bit result. Evidence, the robot's 8-bit microprocessor cannot process this extra bit, explanation, causing the arm to freeze and drop the industrial payload. Link. Which one follows the Peel framework? If you guessed B, you are spot on. Whether it's an embedded system in robotics or a banking network, the context is king, and showing these links helps you remember why we choose one method over another.
Now we transition into Act 3, the transformation. We are utilizing a disciplined methodology to craft the perfect exam response. We are going to take Alex and Sam's answers and rewrite them live. Watch as those red pen marks transform into green check marks. We are introducing the Computer Science Success Blueprint. This is where we move from what it is to how you write about it to get full credit. When Alex rewrites his answer using the blueprint, he stops just listing binary-based 2 facts. He starts connecting the fact that a CPU flag is triggered when an overflow occurs, signaling the operating system. When Sam rewrites his answer, he actually reads the command word explain, realizing he needs to provide the why and the how, not just a rushed summary. This disciplined methodology changes absolutely everything.
By walking through these exact steps, you diagnose the demand correctly instead of writing down everything you know without direction like Alex did. Step 1, identify the exact requirement. This means decoding the command word. Is it describe or evaluate? Step 2, classify the relevant data or hardware. Are we talking about an 8-bit register or a 16-bit register? Step 3, explain the sequence clearly. Walk the examiner through the binary addition step by step, showing exactly where the carry bit overflows. Step 4, connect back to the context. This is the L in your Peel framework, the link. Tell the examiner exactly what happens to the specific hardware mentioned in the prompt. We are putting a 60-second visual timer on the screen right now for your first rewrite attempt. Take a mental swing at it. Follow the blueprint.
What's really interesting about this number, 3, is that it represents the ideal 3-pass revision cycle, securing definitions, rehearsing worked explanations, and finally focusing on exam adaptability with changing scenarios. Your first pass secures the key definitions, like understanding what binary addition actually is. Your second pass rehearses the worked explanations, drawing out the Peel structure over and over. And your third pass focuses entirely on exam adaptability. What if the scenario changes from a retail system to secure communication? Your core binary theory doesn't change at all, but your link in the Peel framework must adapt. This 3-pass cycle is the ultimate way to make sure you are never caught off guard in the exam room.
Let's highlight the classic pitfalls so you can clearly see the difference between a generic attempt and a high-scoring answer. But wait, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the mistakes. We need to look at the classic wrong turns that students make under pressure. Knowing what not to do is just as important as knowing the right framework. We're going to dive into an interactive workshop right now to test your ability to spot these errors in the wild.
Welcome to Challenge 1, Data Scan. We're putting a 60-second visual timer on the screen. I want you to look at these confusing theoretical foundations. Side A, memory versus storage. Side B, logic processing versus arithmetic processing. Mistakes frequently arise when learners confuse nearby concepts. In the context of binary overflow, are we dealing with memory constraints, storage constraints, or arithmetic processing? If you scan the data, you should see that an overflow error during binary addition is fundamentally an issue of arithmetic processing within the CPU's registers, not long-term storage. Dense notes must train this exact comparison. If you write an answer about how an overflow means the hard drive is full, you get 0 marks. You have to clearly distinguish these foundational concepts to extract the core trend correctly. Moving to Challenge 2, Find the Flaw. I'm putting a flawed sample computer science paragraph from Sam on the screen. Let's compare answer types. Side A is vague wording and generic descriptions, yielding low marks. Side B provides process steps anchored to the provided context, yielding full marks. Sam wrote, "The device breaks because the numbers are too big and memory is bad." Can you identify the sentence losing marks? The examiner commentary tells us exactly why this fails. It brilliantly illustrates how writing a specific, contextualized response avoids the trap of just naming a device or an advantage without explaining the actual why and how. Sam used extremely vague wording. He didn't use the term overflow, register, or carry bit. He didn't anchor it to the specific device in the prompt. He gets absolute 0 marks here. Now for challenge 3, speed writing. We have a 30-second timer counting down right now. Your goal is to write one perfect Peel paragraph avoiding these common errors: vague wording, confusing similar terms, missing process steps, failing to answer in context, naming without explaining, and giving advantages without reasons. Keep these classic wrong turns in mind. Don't describe a totally different technology that only sounds related. If the question asks about binary addition overflow, don't start talking about hexadecimal color codes. You must safeguard your marks by sticking ruthlessly to the Peel framework and avoiding these documented pitfalls. The timer is ticking down. Remember, point, evidence, explanation, link. Keep it tight, keep it accurate.
For our final section, Act 5, we are going to present the complete computer science answering system. We are going to build a reliable, actionable memory structure you can use right before answering any exam question. This is your cheat sheet recap, and our progress bar is finally reaching 100%. This final system relies on 3 rules that guarantee top marks. Rule 1, command word decoding. You must know exactly what the question is asking. Rule 2, Peel framework application. You must structure your answer logically. And Rule 3, the time management matrix. Don't spend 10 minutes on a 2-mark question like Alex does, and don't spend 30 seconds on an 8-mark question like Sam does. Let's apply this through our 4-prompt checklist.
First, ask yourself, what is it? Can you clearly identify the concept involved in the specific digital scenario? This connects directly to Rule 1, command word decoding. If the command word asks you to define, this prompt is all you need. What is an overflow error? It is a condition that occurs when a calculation produces a result that is greater than the capacity of the assigned storage location or register. You need to confidently state this without hesitation. This is the point in your PL framework. If you cannot clearly identify the concept, you cannot cast the rest of the spell.
Second, how does it work? Can you explain the exact process sequence so clearly that another learner could follow it step by step? This maps perfectly to the evidence and explanation parts of our Peel framework. When explaining binary addition, you must demonstrate how adding 2 1s results in a 0 with a carry of 1. You must explain how that carry trickles down the line until it hits the final bit. If the final addition produces another carry and there are no more bits available in the register to hold it, that is how the overflow occurs. Your sequence must be totally flawless.
Third, where is it used? Can you anchor your explanation to the exact details of the provided context, whether it's a website, database, or security incident? This is the link in your Peel framework. It's also where the time management matrix comes in. You need to quickly assess the context and link your explanation directly to it without wasting time. If the context is an automated retail checkout system, explain how an overflow error might miscalculate a customer's total bill, causing a system halt. Make it specific to the actual environment they gave you. Finally, why is it better or worse than an alternative? What are the exact consequences, advantages, or disadvantages of choosing this method in that specific situation? Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Being able to evaluate these consequences pushes your answer into the highest marking bands. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. When you can explain why catching an overflow error with a flag is better than letting the system crash, you win the absolute maximum marks.
If you can answer these 4 prompts aloud, you are ready for the exam. If not, it's time to rebuild from the core contrasts and try again. We've taken you from the raw panic of Alex and Sam to the clear, calculated precision of the wizard strategy. We've decoded the command words, applied the Peel framework, and mastered the time matrix. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.